Спасибо всем за подключение. Дарья, вам на русском удобно или на английском? Как легче?
Как хотите.
Хорошо. Ну, давайте тогда официально скажем, что welcome everybody to our next session. This is our 7th day of winter online school within the Spacecom project. And today we have the lecturer on the theme communication constellations, and also a little bit about CubeSat technology continues from the Daria Stepanov from Exolaunch company. Daria, if you're ready, floor is yours. Пожалуйста.
Yeah, thank you very much. I'm just gonna start the screen sharing. You see the screen, right?
Yes.
Okay, great. All right, good morning, everybody. I'm really happy to see you once again. This is going to be our second session, second day today. And I'm going to split it into big groups. The first would be, we'll continue the discussion about CubeSat engineering. And today we're going to go deeper in subsystems, and we'll see how these subsystems interact with each other, how do we go through design process, and what are the differences between different approaches in this design. And the second part of the lecture will be dedicated to communication constellations. There we'll see what's the current state of constellations dedicated for communications. We'll go through several big constellations which have started back in 90s, and we'll review two of them, and another two we'll see just the current constellations. We'll see what's the difference between them, and we'll discuss the challenges they're going to face in the near future. And we'll start with the CubeSat engineering part. As for organizational questions, I would propose the same concept. We'll have around 45-50 minutes talk, and then 10 minutes break, and that's gonna be repeated 3 times. And if you have any questions, please don't hesitate to interrupt me during the presentation. It would be great to have open discussion. All right. The first part, CubeSat's technology is, we're gonna split it in 7 big topics. The first one is CubeSat structures, then mechanisms. The next would be electrical power system, and what's the components of the system. After that, we'll go to onboard computers. We'll continue with communication systems. The next system to review would be attitude, determination, and control, and we'll finish this part of the lecture with space debris topic. And we'll start with CubeSat structures. Basically, there are 3 major design drivers for the CubeSat structure development. First one is stability, and stability is evaluated as an ability to resist bending moments, some buckling forces, and other deformation forces. Basically, the structure shall be stable in terms of loads which are applied for the satellite during manufacturing, handling, testing, and obviously the launch itself. The stiffness is defined as ability to resist dynamic inclinations and or vibrations, and that's the major design driver for the launch of the satellite. And the strength, the last design driver, is defined as ability to resist static forces without the rupture. Basically, yes, so these 3 design drivers are defining the materials which are used for structures. They're defining the structural approach. How do we, the shape of the outer of the satellite and inner parts of the satellite as well. There are 3 basic big blocks in the structural hierarchy. The structure for CubeSats is divided like by the primary. This is the cube you can see below. So that's the main rails and the brackets which are connecting these rails. So this structure carries like the major loads during the launch, and basically it has to carry like the launch loads. In other words, like as we remember, based on the CubeSat design specification, these rails are the only interface between the satellite and between the deployer. So all the loads are affecting the satellite like from sides, from all the sides, and they're influencing the rails. So basically these rails and the structure which is connecting these rails shall be as stiff as possible. The second part of the structure is the secondary, basically. This includes thrusters, panels, booms, antennas, and the components which are not really carrying the loads. That might be also like some brackets inside the satellite, which are stiffened enough. And yeah, on the picture you can see some like hinges for solar cells or antenna holders. And the last one is territory. These are components housing, brackets, fasteners, and other additional mechanical components. That's basically here what can be mentioned, that in our project we are mostly using like commercially available components for housing and for like fastening for brackets. However, we pay a lot of attention in the materials which are used for that components, and conduct some testing prior to using them in our systems. Some of the components we're using can be also done, like they do not need to be made of metal. We're also using plastic ones, but once we're talking about plastic, it's important to remember outgassing parameters of the plastic components. A few words about the primary structure. So that's pretty much the core of the spacecraft, and it's the thing which is interfacing the deployers. It has to carry all the load which the satellite will experience during the launch, and it carries tensile and compressive stress. Here in the picture you can see some like resonant modes of the CubeSat structure. So basically during the launch, satellite can be affected like by this force and by this force, and structure shall carry all these loads and not let the components get detached or get broken under this stress or bending moments. There are a couple of like major requirements for primary structure. So it shall provide load path between spacecraft and the launch vehicle. And as you can see, there are two bending forces. So the structure needs to accommodate these forces in a like optimal way. It's a mechanical interface to launch vehicle. Yeah, like I've just briefly mentioned that already. It shall also provide access to components and assemblies during ground operations. And for example, one big challenge which CubeSat developers are facing, so these panels are normally covered with solar panels, which is like the last components, mostly the last component to be attached to the satellite. And it's pretty hard to connect like the last connectors to this panel. So the structure shall be designed in a way that all components shall be accessed in a easy and fast way, and all the cables can be attached also in a like easy and fast and optimal way. Structure carries the dead weight of the spacecraft. So besides the launch vehicle, it shall also carry the weight inside the satellite. It shall secure positional stability for antennas and other instruments after launch and under changing temperature conditions. So temperature expanding and shall be also taken into account while designing the structure. Antennas placement and instruments placement is in particular important because because of the radiation patterns and the pointing of the instruments and the mission objects, which can influence the mission objectives afterwards. So the structure shall provide the stability of display, so the antenna shall not be moved away, or the camera telescope also shall not be misaligned after the launch. Stiffness and uncritical natural frequencies shall be also handled by the structure. There are several ways to assemble the satellite, several methodologies which CubeSat providers are using. The first one is the deck mounting. Basically, all the components are stacked inside the satellite, and then the sides of the satellite are closed. Another one is panel mounting. In this case, components, internal components are placed on the sides of the satellite, and the basic structure is not carrying any components, and as during the satellite assembly, all the panels are closed together with components. Here you can see the two examples of deck mounting and panel mounting. Pretty much what I have said in the deck mounting, components placed inside, and these two covers are the last pieces to get assembled. In the panel mounting, a lot of components are placed outside, and we can see a little bit of a mess here with the harnessing and with isolation. Yeah, but basically that's the concept and the idea. Another two ways which were mostly, like, they found a lot of applications in small satellites and CubeSat in particular. These are stack configuration and slot configuration. Stack configuration is something similar to like computers or to like PCs, using some standard connectors as PC104 or some slot edge connectors. Several PCBs are attached for the backplane PCB, and this is later assembled from the sides, stacking components like on top. The big disadvantage of this approach is in the if we need to take like during the testing or during the assembly, for example, one of the components gets broken, or like, there's an urgency to substitute the component. It's required to disassemble the whole stack and then start the assembly process from the beginning. Slot configuration, yeah, is something similar. It's just differs from stack. There can be several slots, and slots are a little bit easier to disassemble. And like you can see the connectors like on this side, and slots are attached to this edge connectors. Yeah, like so regarding CubeSats, here you can see the evaluation of each of the packaging options. Deck mounting is not really suitable for CubeSats because yeah, there's no deck, particular deck in the CubeSat. Stack configuration is the one which is the most commonly used in the satellites, and once all of them are connected, so that's either the ribbon cable backplane or standard connector, which is PC104 style, is used. However, integration and replacements, as I said, requires a lot of additional efforts, as is disintegration. Panel mounting is possible in the small satellites. However, due to size limitations, it's pretty hard to handle. So the panels, they have to be somehow connected, so that already makes it more hard. That makes it harder to develop the harnessing inside the satellite, which brings to the complex wiring. The integration procedure becomes more difficult and most likely irreversible, because once the panels are mounted and everything is connected, it's quite hard to like, break in some connections or break in some attachment points might make the procedure irreversible. Slot configuration is like a really interesting alternative to stack configuration. It uses just the spec plane. And the replacement can be done in an easy and fast way. However, we didn't see like many CubeSats with this packaging option. Mostly, I think due to vibrations, the stack connector can get a little bit damaged. So the big question here, how to ensure the good connection between the board and the connector without advancing too much the mounting of that, and not like making this the stack configuration. We will review some of the examples for the structural concept. And the first one is this Mia Huakai CubeSat from the University of Hawaii. They use the solid structure. You can see there are not so many cutouts, just looks a big piece of metal. However, like some of the advantages are the easy mathematical modeling. So basically, this kind of structure most likely will carry all the necessary loads. It was pretty easy in manufacturing, and integration was easy. However, the satellite itself like became quite heavy, and there is no possibility to accommodate components outside. So basically, once designing solar panels, like all the components of the solar panel shall be on the outside, like all the diodes and connectors, which is not always really easy to make. The next one is the Cal Poly CP1 CubeSat architecture. So this is it consists of two modules connected like with this diagonal shape bodies. It's pretty lightweight. It can accommodate components on the outside and pretty flexible with the inside accommodation. The printed circuit boards of the size of from 100 to 80 millimeters square can be accommodated inside. However, this structure is pretty hard to model and to analyze in terms of stiffness and strength. The integration procedure might be pretty complex, and obviously the manufacturing cost of this shape is higher than comparing to the structure we've seen before. On this one, we see the DTU SAT-1 made by Denmark Technical University. The structure is pretty lightweight. It's a good size. That's standard PC104, which is 98 by 96 millimeters square. However, this structure limits the payload designer with some larger component placement in the satellite. This structure requires higher manufacturing efforts and some costly aluminum alloy because of the, again, stiffness and strength with this shape, if not provided by the structural construction, but shall be done by the material selection. And the complex integration procedures is still here. Another interesting approach was developed by TI SAT. This also looks like just a big piece of metal. This one has a good thermal conducting and radiation shielding. So basically, if like all the sides of the satellite are made of steel or made of aluminum, like provides a good safety for the radiation. It's like really custom made to meet specific mission requirements. So there are cutouts in the structure we can see, which are specifically adjusted for one type of payload. In case there are any design flaws or there is another iteration of the payload and this access windows can change in time, there's a high risk of the structure not being suitable anymore. So the integration procedure might be quite demanding, and the design, overall design might be quite complex. Yeah, this is how it looks. Yeah, there are a couple of mounting points, access windows. However, as I said, like all these parts might be also hard to manufacture. Interesting concept. It was made by ISIS. This is the CubeSat structure. I think most of the CubeSat companies got inspiration from. Like this one is really easy to buy. There is an online shop for CubeSat components, which is similar to the normal online shop. It's available in many different form factors from 1U until 6U and already 12U. It's quite cost-effective solutions. However, customers have to comply with PC104 standard, so the mounting holes for the PCBs in the structure already fixed, and in case the satellite designer wants to use another PCB size, there shall be like another bracket or something which will attach the new design for the structure. There are not so many options for deployables, so the structure tries to accommodate as maximum possible volume in the deployer, thus limiting the space on the outside of the satellite. So, and the share panel mounts are fixed, so yeah, there are not also many options how to adjust the panel mounts. The last, I think, CubeSat structure is made by CubeSat Kit. We see that there is an isogrid pattern which helps a lot to enhance the stability and resistance of the structure. Like side panels might be solid to allow any customer configurations. Basically, this pattern might be changed to some like special payloads. This structure is also available in like different form factors. So basically the structure was a starting point for some commercially available components. Including these shapes in the structure, there is already a limited capability to accommodate custom parts. So in case there is a payload which has some specific aperture looking outside of the satellite, it shall comply with these cutouts. Size accuracy restricted by use of bent metal sheets. So as these sides are sheets made of sheet metal, there shall be other structural components like these main brackets, top and bottom, which has to carry all the loads. And again, limited options for deployables. Oh yeah, and as you can see, the CubeSat structure that we are providing has been inspired by this isogrid pattern. It consists of small number of parts and pretty easy in integration, lightweight and high stiffness. We're making it from aluminum alloy, which helps us to achieve the high temperature stability. From the disadvantages point of view, it's also mostly carry the PC104. There are some brackets available for other types of other form factors of the internal components, and low integration density is also one of the disadvantages of our structure. A quick summary on the structures. It has to be made out of aluminum for good thermal properties and the good interface matching in between the satellite and launch adapter. CubeSat configuration is actually determined by the primary structure. So that primary structure sides, apertures, openings are on one side are defined by the payloads and by the systems which are in the satellite. However, they also dictate the composition of the satellite and their placement. Many CubeSat projects develop structures on their own. That's true because the structure is not the most complicated component of the satellite. So like many manufacturers are pretty free to design it by themselves. From some interesting points, approximately 20% of total mass of the satellite is due to the structural elements. So they tend to be over-dimensioned to limitations in manufacturing small wireframe structures. So composite materials, there are some structures made of composites, and I think there were several experiments launching the composite structures. However, it's not as publicly utilized as I think it might be in a couple of years. For CubeSat structures, launch loads like sinusoidal, random vibration, acoustic, and shocks are pretty much harmless. So that's due to the design approach and material selection. In case one day you'll decide to build your own CubeSat structure, there are a couple of things to remember. In case you want to do it by yourself, it's pretty simple and easy in the design. Tolerances are quite relaxed compared to like some other systems. If you're making it by yourself, you can easily change and adapt it to commercial solutions or get inspired by them. The material selection will later influence the coating options. Here, yes, regarding the coating, I think we discussed it last time. So the rails shall be anodized to prevent the welding in between the deployer and the CubeSat. And the structure shall be also optimized for thermal conduction. Some of the important notices are also that the structure shall not be designed as like the first part of the satellite project. It's always good to have this back and forth in the design where the electrical or the payload components are integrated in the structure in CAD, and 3D model is being adjusted. So in this way, it's much easier to prevent some like big mistakes of components not fitting in the structure of the satellite. Integration procedures shall be considered during the design. So basically, knowing how to assemble the satellite early enough in the satellite project is also a crucial part. Accounting for the long lead times might be helpful while iterating several structural designs. And like as we know, sometimes components can be delayed, and in terms of structure, I think based on my experience, that was the component which was delayed the most of the time. So it's also necessary to have like additional timings when it's possible to delay a little bit the finalization of the structure. All right, basically, so there are these steps in structural design, so design or redesign, manufacturing, coating, finalizing, assembly, and integration. This is the flow of the structural life in the CubeSat. And with this, we are going to the second topic, which are mechanisms. Do you have any questions so far regarding the CubeSat structures? Or everything is fine?
Okay, thank you. Is there any questions?
Okay, if there are no questions, I'll continue with mechanisms.
Yeah.
There are a couple of types of mechanisms in the CubeSats, and the first one, all the CubeSats shall have, based on the CubeSat design specification, are deployment switches. These are really like small sub-miniature micro switches, which are attached to some spring mechanism. Like basically you can see it over here. This is the structural components, the structural side. This is the rail, like in the cross section of the rail. This is this micro miniature switch, spring, and some. It can be screw. It can be just some cylinder made of metal. Yes. So like once the satellite is in the deployer, this switch is pressed, and the satellite battery is detached from this from the rest of the components. When the satellite is deployed on the orbit, this switch gets unpressed, and basically the battery then is connected to the main of the system. So this component, every CubeSat shall have and shall like accommodate either in the rail side, or like it shall be somewhere on the rail, because there shall be connection in between this mechanism and the deployer side. And here, like you can see the internal parts of the switches. The next one is the solar panel hinges, or solar panel deployment mechanisms. You can see several times folded solar panels. Basically, this is like pretty easy mechanism. Hinges are also supported by springs, and the panel is folded several times. And then the mechanism, which is really similar to antenna release mechanism, which I'm going to talk about in a few seconds, is used. And once on orbit, this mechanism is activated and the solar panel, due to the spring forces, is deployed. Antenna release mechanisms for CubeSat, there are several types. Most often it's electrically powered heating wire made of some nichrome, and it's pretty much the antenna is attached to some either like plastic or any type of the material part with this nylon string. Once on orbit, this the wire is heated and the nylon filament is melted. On this picture, you can see the example of the BSAT antenna release mechanism. Instead of heating wire, like this nichrome heating wire, it's possible also to use some resistor or any other component which can be warmed up pretty quickly and does not outgas so much. So that was the pretty easy, pretty fast, really easy to reinstall mechanism approach. There are more interesting antenna mechanisms. For example, this one is accommodating up to 4 antennas of different lengths. All these antennas are stopped inside this really small compartment. But inside of this compartment, absolutely the same approach is utilized. So there's also the melting wire and the heater, which are activated at some point, and then due to the spring forces in this part, the kind of the legs of the antenna release mechanisms are opened. This mechanism is a little bit more difficult to handle and to reinstall. However, it's quite small in the shape and can accommodate up to 4 antennas. All right, that was briefly about the mechanisms, and from here we will continue with power control and distribution system.
That about the parts. There was a question about the solar panel.
Okay.
Is it same? I mean, the normal one, or it is special solar panels?
You mean solar?
Yep.
These are standard CubeSat solar panels. Basically, the solar panels normally use space-grade solar cells. There are 2 big companies which are providing the cells, which is one is Azure Space, another Solar. Yeah, I mean, most of the CubeSats are using this kind of solar.
But they are not the same with what we are installing in our houses.
I know these yes, they're really different. The ones we're installing in our houses are much cheaper. They use this different technology. They're mostly like one-time junction, and these one are triple junction gallium arsenide cells. They have up to 30% efficiency, and the ones we're using on the ground are most of the time like 15 maximum or 16 percent efficiency. Like I'm going to talk about that in the electrical power system, but solar panels are one of the most expensive component of the CubeSat, and it's better not to save budget when we're talking about electrical power system and solar panels, especially, and communication system. I think there were CubeSats which were using like more relaxed solar cells and solar panels. However, like with double less efficiency, you have double less power in the end, and it's either experiment takes more time or there's not enough power for the mission and for the experiment. So the solar cells shall be like really good quality and really space grade.
Can you give us the names of the solar panels? So types or?
So this the solar cells, for example, we are purchasing solar cells from the company called Azure Space.
How? Row space?
Azure space.
Azure space.
Yes.
Okay. Thank you.
Yeah. However, like in Azure space, they're selling just this solar cells components, but then like all the solar panel has a little bit more complicated designs. For example, the protection from the solar cell failure, the maximum power point tracking, the thermal control, and so on. So, like at our company, for example, we're taking like the cells and we are providing the design of the solar panels of different like shapes and so on. And yeah, they're pretty much every CubeSat company is doing that. All right. The next power control and distribution system. But there are four main tasks the system is doing. First one is the conversion, storage, and the distribution of electrical energy. And here we remember such components as solar panels, batteries, and control modules for distribution and processing. Acquisition of system health parameters. As soon as the power is distributed between systems, it's also required to get a feedback about do they consume like enough current, or is there some anomaly which makes them consume more power than was specified. Operations of switches and systems monitoring are the third and the fourth one. So general requirements for the power control system are listed here. EPS shall provide a continuous supply with electrical power. It shall control and distribute electrical power between payloads and the main bus. It shall support requirements of peak and average power. For example, once the communication modules go into transmit state, or there is some system which is turning on, draws a lot of power, like current at that moment, power system shall take this into account and either smoothen or prevent from turning on the system. It shall provide telecommand capability for systems control. Basically, that means that we shall be able to send a telecommand to turn on or to turn off the system. It shall provide telemetry capability for system status. That includes like power consumption. Is the voltage level correct? Is there any fault in the system switch? Activation and deactivation of assemblies, protection of spacecraft against failures of the power system, and here we shall also consider redundancy in some of the main components, avoidance of single point errors and redundancy strategies. Basically, that's what I just said. The EPS shall also consider orbit type, like in terms of height and inclination, that will influence like the solar cycles. Mission length planned, this mostly influence the batteries charging and discharging cycles. Solar array pointing area, and so on. So these were like system requirements. If we're talking about mission specific requirements, there shall be type of the power supply bus. There can be several types. Bus voltages, these are normally like 3.3 volts, 5 volts, unregulated, and 12 and going higher already. Energy and power demand in different satellite operation modes. That's we're gonna see a little bit close in the next slide, but that depends on the number of active components and their duty cycles. Type and amount of system health statuses, measurements, values, and this includes current voltages. It can include also temperatures. Yeah, these are most commonly used. And we'll not go into detail of like every of these requirements, and based on this example power control distribution unit from the satellite, we'll see how the design process is and how do we go through all these requirements to get the proper system working in the end. So basically there are three main blocks in the EPS, how we just discussed. The first one is conversion, so the power comes from solar panels normally in CubeSats. The storage, which is the battery, and generation and processing and distribution units. In order to increase the reliability of the system, the additional redundancy is added to the system. Here we can see there are 2 batteries. Solar panels are supplying the chargers with 9 volts voltage, like the power level of 9 volts, and the battery are supplied from the solar panels with the solar energy through these charge regulators. We need DC to DC converter here because I think the output of the solar panels in this case was like 4.2 volts. Thus, we need to boost the voltage level a little bit up because it has to be higher than the maximum battery voltage. Charge regulators are this kind of autonomous switching units, which based on the voltage and current level from the solar panels and the charger, like the state of the charge of the battery, which is most of the time it's just like the voltage level of the battery decides either it's time to charge the battery or it's the battery is completely charged. Then from the charger regulator, the power line goes to 2 converters, in our case 5 volts and 3.3 volts, and each of these power buses is then supplied to the switches. As I mentioned, here are the solar panels and solar cells. We are purchasing them from Azure Space Company. The triple junction gallium arsenide solar cells with 30% efficiencies. We're using in this satellite the configuration of 5 panels with 2 cells on each, and 1 panel was accommodating 8 cells, but that was like more experimental thing. In this kind of small CubeSat, the available power was around 2 watts, and that was like pretty much enough for all the experiments we wanted to conduct. Here you can see also how the solar cell itself is looking. Right, so that's the datasheet screenshot, which shows what are the parameters of the solar cell. Average open circuit voltage is 2.5 at the beginning of life, and average short circuit current is 16.9 milliamp per centimeter square. So if we calculate the area of the cell, we'll get the average short circuit current. There are also some temperature gradient characteristics, which are also important to include in the power budget analysis, for example, because the efficiency of the solar panel, like not the efficiency, but the curve which connects voltage and current of the solar panel is influenced by the temperature. And as we see, the solar cells are black, so they might get pretty hot in the sun. This will also influence the power on the output of the solar cell. Regarding the batteries, here you can see the battery type we were using before in our satellite projects. This is the Varta micro battery with nominal voltage of 7.4 volts. It's based on lithium polymer technology. And the capacity of 1 block like that is more than 1 amp hours. The critical thing here is the battery can be charged when the temperature of the battery is more than 0 degrees. In order to prevent the battery failure and charging in the cold, we're also adding some additional like heaters and temperature monitoring in the battery pack. Maximum storage energy of 2 battery packs, for example, which are used in the satellite, this BSat was 19 watt hours. Basically, 2 battery packs were used. Power control unit is the unit which is responsible for processing and distribution of the power. It is based on 1 microcontroller, which is controlling all the switches. It gets the information about switcher states and power consumption of all the modules through analog digital converters. In that case, it was like 16 channels on each converter. There is a circuit with integrated watchdog, which is helping from the latch ups during on-orbit operation. The basic principle of this system is following. The main switch is controlling the power coming to this microcontroller, and the watchdog has a specific period of time where it shall receive the signal from the microcontroller. If it does not, it resets the main switch, basically enable signal, and main switch does not feed power to the microcontroller anymore. In this case, in terms of, in case of microcontroller failure to send the signal to watchdog, obviously something has happened and the power of the microcontroller is reset. In this way, it's possible to save the microcontroller in case of some particle event is happening. The microcontroller is also connected to two CAN buses. There is a redundant CAN bus introduced in the satellite, and for that there are two transceivers installed. And this one, you can see the first prototype of this control module. It had 24 switchable components for turning on and off external systems. Via CAN bus, it was possible to set the default onboard computer parameters, choose internal external software images, set ADC thresholds, activate or monitor these thresholds, and set the PCU clock. So the request for these values was done from the onboard computer via this redundant CAN bus. And this was already the final design of the system. I think it looks much more prettier. In several design iterations, we achieved that this system can be suitable for 1, 2U, and 3U CubeSat designs. So here, the DCPS can control up to 16 power buses, features power distribution unit, yes, with this 16 buses. It is really failure tolerant, and it monitors every channel. You can set up the channel parameters via the software. Power switches can be configured to different power buses and different voltage levels. Main bus is independent from the power control unit and cannot be switched off in case of failure. So that means if the main microcontroller of electrical power system is failing, then the power channels which are selected will be still operating, and it will still be possible to get signals from the satellite. On this slide, you can see the updated EPS block diagram coming from this prototype to this system. What has changed? We still have solar panels controllers. The power here goes to bypass load switch, and through this load switch, it feeds the power control unit, the unit with microcontroller, watchdog, and yes, CAN transceiver. We also added the I2C isolator to expand the amount of interfaces available. So the second power line goes to the load switch. That's the main switch which activates or deactivates all the satellite subsystems, but the power control unit. Here there's this boost converter for 9 volts and the battery charger and the battery connector. After that, the power either from solar panels or the battery is coming to the system load switch and to the power processing module. Here there are several connectors for 3.3, 5. There are also several references, voltages, levels, or unregulated voltage can be put through the system, through power distribution system to the switches assemblies. Besides these 8 switch subsystems switches, there are also dedicated sun sensor switch, antenna release switches, and magnet Docker switches, which are going then to the system connectors. And here I think we can make a short break, like 50 minutes of the lecture have passed. Would that be fine?
I think yes, but here one more question. If you saw, what type of battery recommended to use in CubeSats?
So lithium polymer.
Okay. So it
Yeah,
is also some kind of specially designed, or?
These ones are not specially designed, they're commercial off the shelf. So we do not put much effort in or much resources in purchasing some space grade batteries. However, we provide the comfortable conditions for the batteries in terms of temperature, in terms of battery monitoring, so in terms of charging. Yeah, so like some batteries have a specific charging profile, and we try to put more effort in designing proper system to work with these batteries.
Okay.
It is explosion free. You never had any problems with explosions. Yes. Yeah.
Okay.
So yeah, there are.
Thank you.
My question.
Yes, Dr. Ege?
Excuse me. My name is Bakhtiar Palwanov. I am a physics and research in semiconductor structure. We are using in preparing solar cells. I have one question. Можно на русском вопрос?
Да.
Хотел узнать, какой параметр КПД солнечный
Сейчас немножко
коэффициент полезных действий
перебивается связь, я плохо слышу.
У нас интернет очень неустойчивый работает.
Какой параметр КПД? И дальше я не расслышала.
Да, вопрос, пожалуйста, еще раз.
Время использования этого солнечной панели. Вот.
Да, но в принципе у всех солнечных панелей есть такой beginning of life и end of life. И end of life зависит от конца миссии. Наши миссии, например, они рассчитаны на 2 года, и просто в дизайне power budget и расчета энергетических характеристик мы учитываем вот эти 2 года. В дата-шите, который предлагают производители солнечных ячеек, в принципе, указаны вот это end of life параметры, и они обычно там, не больше 10% за 2 года. Так что, надеюсь, это ответ на ваш вопрос. Или я просто не расслышала что-то.
Ну, если у вас будет вопрос, то просто напишите.
Хорошо.
Спасибо.
Да, хорошо, тогда можно 8 минут перерыв, и тогда в 10 минут соберемся еще.
Хорошо, 10 минут.
Угу.
Спасибо.
И у него нет какой-то конкретного срока годности. Здесь есть в таблице Electrical Data Typical есть характеристики, насколько они ухудшаются со временем. И вот эти характеристики мы используем во время наших дизайнов. Можете сюда посмотреть. Так, я тогда возвращаюсь к...
Да. Я просто хотел сказать спасибо.
Да. So we continue with the next chapters about onboard computers. So there are several requirements which we are taking into account while designing. So there are operational requirements, functional and interfaces and protocol requirements. From the operational requirements, it's important to take into account operating modes of the computer and like draw this phase diagram of different states of the satellite. The OBC shall be autonomous, fault resilient. It was a fault detection, installation, and recovery. From the functional requirements, there should be system run control. So basically, OBC shall collect all the possible telemetry about the satellite, which is IPS is not collecting, and run control over the states of all the modules. The control shall be done also not on the subsystem level. OBC shall process the clock, so that's the source of the clock on the satellite. It shall be input and output for the data processing. Basically, it can be applied in terms of attitude control algorithms. For example, the sun sensors data is processed and the output data of quaternions about the satellite orientation is on the output. It shall communicate with subsystems and all the components. It shall provide data storage and so on. Functional requirements can be really like mission dependent, and there can be a huge list of these requirements. Regarding interface requirements and protocols, it shall be compatible with hardware and software interfaces and standards and protocols of all subsystems. And it's also good when it's compatible with like basic satellite standards. These are hardware components of the onboard computer. In the core of the system, we have most of the time powerful microcontroller with a set of digital like input outputs to control like either switches or like other something else. There are several blocks of memory, program memory, data memory, and like general memory, which will be protected from the latch up. There's also the watchdog, power and reset, communication, and debug port modules in the onboard computer. Regarding interfaces and buses, there are several architectures which we are considering. So like device-to-device communication, that's normally done with the payloads when we don't want to include them into the main bus, and this can be as RS-232 or SPI, or it can be the bus architecture where there are several devices on the bus, which is already RS-485, I2C or CAN. So we use for like this centralized and decentralized architectures together in the satellite, depending on the payloads and subsystems profiles. With master-slave communication, you can get like 1 megabits per second on CAN or up to 60 megabits per second with SPI. So yeah, that's pretty much covers all the requirements for like high-speed data downlink or inter-systems communication. While in standard satellites, signals have to be transferred over the long distances. Harnessing in the CubeSat is pretty straightforward and pretty short and pretty simple. So there is no need in additional like isolation to increase the length of the cables. For distributed architectures only, and here like you can see the example of the CubeSat, there are a couple of specifications proposed, this mill and Tokyo passing. But in terms of their utilization, like you can see point-to-point connections, this one can be used. However, even though there are like many protocols and many like physical layer protocols are available, most of the CubeSats are using either I2C or SPI or CAN buses. Yeah, so that's the simple architecture of the CAN bus. Or RS-232, we're mostly using with the payload providers. We have like quite sophisticated CAN protocol, which not all the payload providers can follow. Thus, RS-232 is like much easier for them to install in their systems. Some of the responsibilities of onboard computer is the measurement and storage of housekeeping. So the parameters which are not collected by EPS measured and stored in the OBC. It's the main, it's the master of the CAN bus. It's the master of like I2C and SPI bus, and like it's also handling the CAN bus. It stores several software images, and for example, in our architectures, OBC is normally storing 3 software images, where there's a possibility to update one of them, and in this case have the reliable software update feature. And execution of software tasks, for example, processing intercommands and telemetry, navigation and attitude control tasks. If there is no dedicated navigation and attitude control system on the satellite at that moment, OBC can also like handle them. Monitoring of health status of the payloads and managing the satellite modes, running the real-time clock, and performing the software update features. Again, let's consider like the block diagram and to see the example design of standard onboard computer. The core is in the microcontroller. It has several memories dedicated for either storages or for advanced computations, so SRAM and the flash memory. Normally we have, first of all, redundant flash memory, and we also like put the cover on the PCBs to save it like from, to provide some security from the radiation. There's the same watchdog architecture with a main switch to protect from the latch-ups. There's a internal flash memory, like not internal, but the flash memory dedicated for only the satellite purposes, while this one is dedicated for satellite purposes, while this memory is more like performing as mass memory storage for payloads. There's several analog to digital converters which are taking the, which are in charge of telemetry collection from the satellite, and also 2 transceivers for 2 redundant CAN buses. Key components of the satellite, its microcontroller is ARM-based, 32-bit RISC architecture. The clock is 60 megahertz, which can be boosted up to 180 megahertz. Has 12 kilobytes of static memory, 248 kilobytes of non-volatile memory, plus like 16 megabytes and plus 4 megabytes, and dual CAN bus connection. It has 3 external converters with 16 channels each. It can monitor external supply voltages. It has external watchdog with a shutdown capability. It can be programmed either via SPI or GTAC, and it's pretty low power, which is 150 milliwatts only. So that's a pretty efficient architecture in terms of computational capability, memory capability, and power characteristics. Regarding the housekeeping, this OBC can do 24 currents monitoring and 4 sun sensors handling. It monitors 2 voltages level, 8 additional currents from payloads, 3 rotational rates, 6 magnetic fields vector components, and 11 different temperature values. These are basically the telemetry values from the satellite for the mission, for one of the missions. Housekeeping is stored from the PCU, TNC, and PDH. So it's using the external memory for that. Basically, OBC is collecting its own telemetry, PS is collecting telemetry about the power consumption of all the satellite modules, then transferring these to OBC storage, and OBC stores all this housekeeping data inside. This was the first prototype of the onboard computer. So this was carrying 2 redundant kind of architectures and redundant TNC module. It had like 3 gyros, one on the each axis, giving some information about the attitude determination, together with 2 magnetic field sensors. It had a debug interface and a set of connectors. And this is the, so if this also was the first prototype of the system, this is already like the final ready product. It's PC104 based. As for controller, STM32F4 is used. It has 3 non-flash memories with radiation protection, non-volatile space-grade SRAM, and native S-band transmitter support for high-speed downlink. So it was developed back in 2014. There are like several redesigns already to boost the computational capabilities and memory characteristic of the OBC. And as this onboard computer can be used only for like 1, 2, 3 unit CubeSats, like the versions we have right now can be already used for like bigger missions of 6, 2, and 12 unit satellites. This is the updated architecture, which, yeah, another region of the architecture, which you saw on this blue image before. The STM32 controller is in the core, and all the peripherals are located around it. So the flash memory, analog to digital converters, several other converters, watchdog, degrees of freedom sensors, and SRAM, real-time clock, and so on. Any questions about onboard computers? If no,
Can we continue?
okay. Yeah, communication system. Let's go briefly through CubeSat communication systems. Basically, the main task of this is to provide telemetry, tracking, and command capabilities for the satellite to safeguard the communication between satellite and the ground station. So subtasks of the system is to modulate and transmit the telemetry, generate and track the carrier, receive and demodulate the carrier, detect data bits, synchronize them, forward clock and commands to the main bus, and range reception and transmission signal quality. There are several architectures which are used in the CubeSat world. Point-to-point, it's either direct ground station and the satellite. It can be done via relay satellite. This architecture is not as spread as a direct or broadcast data communication. This one like almost not used with the CubeSats due to complexity of the communication system. Another approaches for point-to-point can be direct downlink during data collection. So that's the one we're using most of the time. Direct link after storage of data. This as for example, our satellites are mostly located in the polar orbits. We're not using, we're not having the direct passes over the ground station every time. Like, not every orbit gives us the access to the satellite data. So yes, sometimes the storage of data before the next communication session is required. Yeah. And we actually have used the broadcast to several ground stations in the past. That was done when we had like a little bit of trouble with our ground station. So our partner ground station was working for, like, we both were working on the reception, so the transmission component of our ground station was not functioning properly. So basically on our side, we were mostly listening, and the ground station of our partners was also listening and giving the comments to the satellite. So I can say that the broadcast architecture was also a part of my experience working with CubeSats. Regarding the data relay, there are like, once we go to this constellation topic, it's pretty hot, like, architecture nowadays. However, in the CubeSat like industry, I think this is like overcomplication to the system design, and most of the CubeSats do not need this functioning. Like if we're talking about the relay, so the satellite then needs to carry several transmitters, shall point, like perform maybe complicated pointing maneuvers, which is in case of small satellite might not be needed. It's sometimes it's more like it's easier to utilize several ground stations than enhance the capabilities of the small satellites. These on this slide, you can see some of the key components of the transceiver, or the first version of the transceiver we were using. So it was at 90 CAN 102.8 based. It used CMX modem. Basically we didn't have to do this modulation, demodulation in external circuits. The transceiver was BK77, and it also carried 2 CAN transceivers to communicate with the main bus. Yeah, like before we go to the transceiver redesign or mission design, we obviously calculate the link budget, and here you can see like the sample of the link budget we're normally doing. All right, the next system which we're gonna briefly discuss is attitude determination and control system.
Sorry, there was some questions on the
Yeah, sorry.
About which radio model or technology uses to communicate with CubeSats.
All right, so the most used frequency band, for example, is the UHF or VHF, and we're using like antennas, like monopole antennas, where the satellite does not need to be oriented. We're normally using 2 UHF modules to provide like the full coverage, like the full sphere coverage on the satellite. That's used for telemetry and telecom. And if we're talking about high-speed communications, the S-band transmitters or X-band transmitters are the most common. There are a couple of projects which are using K-bands. However, instrumentation for this high-speed bands is already much more complicated, and especially antenna design is much more complicated. If in X-band and S-band we can use still patch antennas or like helix antennas, K-band requires additional investigations. Yeah. Another really interesting technology, which is I think it's on technology readiness level 7 already, is optical communications, and that's actually my personal field of interest. Optical communication has like lots of advantages, and we will talk about it in the last parts of lecture. But it has like lots of advantages in terms of terminal size, power characteristics, and transmission speed, security, and so on. However, right now there are only like prototype modules built for this, and it's not like so widely spread. So the most used is still UHF.
And also about hardware, I mean, stabilization technique is on the CubeSat.
Excuse me?
Stabilization techniques. How the CubeSat stabilizes itself.
Exactly. That's what we're going to talk right now.
Okay.
Yeah. So attitude control determination system requirements. First of all, shall consider what pointing orientations shall the satellite like be on orbit. And there are like a couple of modes which couple of attitude control modes. First one is the tumbling. Once in orbit, satellite like gets some initial speeds around 3-axis, like some angular speeds from the deployment, and like taking all these forces into account, it's basically starts spinning once in orbit. And the first mode is to detumble it, to make it more or less stable and rotate around like one axis at least. Then the safe mode is the mode which will still allow the satellite to be oriented correctly. For example, if there are deployable solar panels, they shall still face the sun. In this case, the satellite can be tumbling, but the mission critical parameters shall be taken into account. Then there are inertial pointing mode, nadir pointing mode, and the most advanced target pointing mode. Here in the picture you can see inertial one is when the vector, like the z minus vector, is collinear. Basically, it doesn't change its orientation. In nadir pointing mode, satellite must track, like the z plus of the satellite shall be always pointing the center of the Earth. And target pointing mode is the mode when the satellite is doing pictures or is connecting to the ground station. Basically, the satellite shall be targeting one point on the Earth. It's like on the design process, after all these orientation states were defined, operational modes of the attitude control system shall be defined. So there are three characteristics of that. First is the task, what for this attitude control mode is required. This includes like downlinking, targeting the some field or some spot on the Earth for imagery, and so on. Accuracy parameters, so how accurate shall be the pointing, and which sensors and actuators can be used in the satellite. So while defining these modes, the following principles shall be taken into account. So the spacecraft can be in two modes at the same time. Modes shall allow the design to complete conditions with the equipment the satellite has. For example, if there are magnetodoggers, obviously it's not going to be possible to perform three-axis maneuvers. The position of spacecraft shall be completely controlled by the attitude control system, and each control mode can be controlled by commands, either from onboard computer or from Earth. Here are some of the examples of attitude control modes and their connection. So the suspend mode shall be reached from every state from suspend mode. The next one is auto acquisition, and here we can go to damping. Damping only can bring us to large angular maneuver, and from there it's possible to achieve with a sign pointing, fix or rotate, inertial pointing, or nadir pointing. Right, here we can see like one orbit example and all these pointing regimes and how do they change in time. Yeah, so if you find this is the first suspend mode regime. So in this case, the attitude control starts performing like all actuators are disabled, and once we go to the next auto acquisition, which is here, this is the safe mode, and solar rays are pointing to the sun. In sun pointing mode fix, here you go. The solar rays are still pointing the sun, and attitude is internally fixed. In sun pointing mode rotate, the satellite is able to rotate around this axis, which is z axis. Earth pointing mode is visualized here. So in this case, there can be some instrumentation pointing nadir, or some remote sensing operations can be conducted. In inertial pointing mode, you see the attitude is fixed. Basically, the satellite has the same attitude. Large angular maneuver is done here. So it was done in order to come to the sign point in fixed orientation, and in the damping mode, the rotation from Earth pointing mode was stopped. Basically, here are the examples of how modes go from one to another. All right, just a second. After the satellite is in orbit, so there's no spacecraft, basically attitude control. The simple spin stabilization is required because satellite is tumbling. Like the speed of tumbling can be really high and can influence even the communication with the satellite. The acquisition, so in this mode, initial determination of attitude is conducted. This mode can also be used to recover from power upsets or emergencies or breakdowns. In the slew mode, rotation of the spacecraft is defined with a safe regime, and it's combined with the restrictions of operation and power consumption. In Earth pointing mode, the satellite points to Earth and instruments, and the sun pointing mode, it points to the sun with largest solar area. So after all these orientation, pointing regimes, and pointing modes have been defined, we need to define like what's the accuracy and what's the mission requirements. So accuracy shows how well basically the satellite can point, and the range is defined by angular motions or accuracy which can be held. This is yes, also an another 3 parameters to control at jitter. Once we're using some rotation mechanisms, there's always a probability that something will vibrate, and this jitter, for example, can influence the quality of imagery taken by the satellite. Drift, it's a low frequency motion of the satellite. We should also take into account once we are designing the attitude control system. And the settling time, it's the time when the satellite returns from the maneuver to this upset state. Yeah, maneuvers basically is the systematic change of orbits or attitude parameters. It is specified by angles, rates, direction, duration, and frequencies. An example of the slew maneuver can be like 180 degrees slew maneuver with the rates 1 degree per second around that axis for 3 minutes every day. The attitude of satellites is subjected to disturbances, and these are gravitational forces, atmospheric drag, solar radiation pressure, magnetic field, and some internal disturbances generated by mechanisms or rotating devices like reaction wheels. Also, important step in designing attitude control system is to define the coordinate system, and I think we know some really crazy examples when the launch vehicles were failing due to the fact that coordinate system of the launch vehicle was defined in the wrong way. So yeah, that's a pretty important step. Then there are several approaches to provide active attitude control, and there are several types of actuators. These are coils, flywheels or reaction wheels, and jet engines. After we define the control, the actuators, we need to also define sensors based on which we're gonna estimate the orientation and control electronics to control the actuators and collect the data from the sensors. This is for the active attitude control. For passive attitude control, it's possible to use the boom or magnetic stabilization, where just a big magnet is installed in a satellite. Here on this slide, you can see some of the typical sensors and their parameters. For example, internal measurement, U rates, data rates, they're pretty heavy and might not be utilized on small satellites and have pretty big power consumption, while sun sensors have much less of the accuracy, but they're much lighter and consume much less than 1 watt. Star tracker, they're also quite accurate instrumentation. Current star trackers are much less than 3 kilograms, especially like for CubeSats, and they're much less power demanding. The horizon sensors, magnetometers, or GNSS receivers, typical attitude sensors. A few like really briefly about the approach for sun sensors functionality. So the sensors we're using are these PSD sensors. This is the sensor. This is the hole, which is a hole, the through hole. Once the sun is passing through the hole, it leaves the shadow on the PSD sensor. Sensor generates currents, and based on the currents, we can evaluate these two angles and then estimate the two angles of projection on the sun sensors. There can be 7 digital sun sensors, and these openings can be done in a really advanced and a tricky way, thus giving more information, not just like several currents, but much more currents, and the precision can be much higher. Star tracker is pretty much the optical thing with SSD and microprocessor on the back, and the picture of the stars is compared to like the picture of the taken by the camera, and misalignment is compared, and the angles also, like two angles are relative to each other, are calculated. Infrared earth sensors, you can also see the principle. So basically the infrared shadow or pattern of Earth is imaged using also the CCD matrix, and the deviation from the center is evaluated. Yeah, here you can see some advanced dual infrared sensors in their physical diagrams. In terms of attitude control performance, there's a normally pretty simple controller. We have desired attitude, we have the attitude measured by the sensors, we feed the signal to controller, which controls actuators and changes the spacecraft dynamics. There are like several ways to provide the stabilization. The most used one is the 3-axis, and this covers most of the applications. This can be done using the flywheel, reaction jet stabilization, momentum wheels, reaction wheels, stabilization control, momentum gyres, or solenoid coils. And in this one, you can see the summary of the stabilization types, the accuracies, and like some remarks. For example, spin one is pretty passive, simple, low cost. Reaction wheel-based stabilization has higher accuracy, higher flexibility. It's possible to perform quick attitude changes. However, it's a little bit, it's more expensive, and the better jitter and vibrational profiles from reaction wheels are, the more expensive they get. Body stabilization, it doesn't have pretty much flexibility. It can be accurate, but it's also expensive. Using the reaction jet, quick attitude changes of large systems can be done, but compared to the other types, it's like absolutely expensive and mostly not used for the small satellites. Gravity gradient is the less accurate from all of them. It's passive, simple, and inaccurate, but it's sufficient for some small satellite missions. This is the reaction wheel assembly, for example, we've been using in our projects. It's built by our partner in Berlin. Yes, you can see here the 3 reaction wheels in the pyramid architecture. The integration of 4th reaction wheel provides the redundancy in terms, like if one reaction wheel is breaking, for example, there's another one to substitute it. Yeah, it's pretty compact and pretty small assembly, and can be installed in CubeSats, like starting from 3 units and up to 6 units. This is also the star tracker, pretty compact and pretty small. It doesn't have a flight heritage so far, but pretty accurate and can be used on board of the small satellite mission. These are two reaction wheels for smaller and for bigger satellite, built by Hyperion Technologies. They built for 1 to 3 unit CubeSat. They have like all the electronics incorporated, like all the drive electronics. Yeah, so they're much. Yeah, so I think this one is for 1 to 3 U CubeSat, and this one is for 6 to 12 unit CubeSat. Like, not possible to see the difference, the sizes, but like it's already like observable once you see them in real life. And this one is the highly integrated, like a system which has first PC104 form factor, several reaction wheels installed in one platform, and the star tracker together. So that's like already the attitude control solution with all the required sensors and instrumentation installed. So that I think it consumes 0.5 volume of the satellite. And with this, we're coming to the last points of the second part of the lecture. This connected to space debris. There've been a lot of really a lot of CubeSat missions in the past, and we'll see later today how many constellations are coming and how many satellites are coming to the low Earth orbit. So people are becoming more aware of growing space debris problem. In 2002, on the United Nations have issued their recommendation that all the satellites shall be deorbited within 25 years after end of life. Some experts consider that 25 years is not fast enough. So CubeSats mostly occupy orbits around 500, like around 400 to like 600, and for the CubeSats which are above 550, orbital lifetime is normally like it takes more than 20 years. So including the amount of rising launches within this 20 years from now, the orbit will be really crowded. Additionally, general lack of propulsion and propellant on board of the CubeSats. Basically, CubeSats cannot perform mitigation maneuvers as the big satellites can do. And the short design lifetime. So CubeSats are normally developed within 1 or 2 years, and around 20% of them are failing. And once the satellite has performed its mission, most of the CubeSats are left without any control. As a consequence, which might come in the near future, of course, deorbiting might become mandatory. But here a lot of experts are also showing their skepticism because it's really hard to prove if you're gonna deorbit or not, even though if you have deorbiting mechanisms on board. There are several main deorbiting concepts available today. First is using the drag. This one has impact only on the orbits below a certain height. So for the CubeSats where on orbit more than 600, that might not work anymore. So the approaches here are sails or big balloons. Another one is electrodynamic tether. So this one uses magnetic field and drag forces that can be utilized in any orbit, but I think it's not as efficient as the first one. And propulsion modules, they basically, the satellite needs to change its attitude, turn on propulsion, and decrease the orbit. Right. And let's go through some of the examples of these systems. So here, CubeSat Terminator tape. It's a compact, lightweight module. It doesn't have to be powered up additionally. It has its own solar panels. Pretty small mass, pretty small size, independent pretty easy. The only disadvantage, it takes the space from the satellite side, thus taking 2 solar cells away. And if we're talking about 1 unit CubeSat, 2 cells, it's already quite a lot. The balloon drag devices, another one, they augment the drag coefficient of the CubeSat, which leads to faster deorbit. Right, you can see on the picture basically this balloon. Propulsion modules, so this one is built by Aerojet Rocketdyne, has quite big mass, quite big size, and might not be suitable for all the CubeSat missions. Yes, and my favorite one is the sail, the huge inflatable sail, which increases the drag force. Sadly, all the missions which were carrying these sails, they didn't succeed, but technology readiness level is pretty close to 9, so technology is almost available. This is the sail. All right, so with this, my part of the presentation is finished, and we will jump on the communication constellations in the next, after the break.
Okay, so 10 minutes, it would be, with our time, 5 past 4. So by your time is
12.
12, yes. Окей.
Да.
5 минут первого будет, правильно? To'g'ridan 5 minut o'tganda ko'rishamiz.
Tushunarli.
Low Earth orbit and on the orbit around the Earth. More than 90 companies or agencies have proposed the satellite constellations. The major fields of applications for these proposals are Earth observation for science and business oriented goals, space observation, and communication. On this plot, you can see the estimated number of satellites launched yearly. So the black dotted line represents cumulative sum of all the satellites together. So non-classified stands for the companies which are not set expected time for this satellites. But you can see how in time the number is satellites is increasing, and by 2026 there will be almost 10,000 satellites on the orbit. As I mentioned, there are main application fields for these constellations. First is Earth observation for weather disaster and fast response monitoring in case of emergencies, and communications, mostly powered by Internet of Things, machine-to-machine application, broadband communication, and Internet. Communication field has one of the highest and one of the greatest potentials. So first of all, on one side we have Internet of Things era, which is requesting the current infrastructure to handle large amounts of data and to guarantee service in any position on Earth. On the other side, there is a potential in weather sciences, safety and security, and fast response in disaster monitoring. Most of the targeted applications are going with different strategies, occupying different orbits, either medium or low Earth orbit constellations, large on small satellite numbers, but basically everybody is targeting the full coverage of the Earth. On this slide, you can see small sat constellations for communication purposes were planned during 90s, and a global star had 84 satellites and eight different places at medium orbit. They went bankrupt at some point, but then got reorganized and still operational right now. So ICO, Odyssey, Skybridge, and Teledesic are also different constellations for communication with from 10 to 840 different satellites which these projects have been cancelled. Iridium is another one which we will review today with 66 satellites. Also got bankrupt and reorganized. Orbcom with 35 initial satellites went also bankrupt and reorganized. From this table, we can clearly see that in 90s there was not enough business potential in the constellations. What's the state of today? From 2010 until 2020, following projects have been announced or been in plan under development. So Amazon-driven Kuiper projects with 3,236 satellites in different orbital planes, like 98 orbital planes on different altitudes is currently under development. And we also know that Amazon is expanding its ground station network pretty actively. So big ambitions and big plans. Boeing has been filling the frequencies applications with FCC. However, the status is currently undisclosed. We know that there are going to be more than almost 3,000 satellites, but there are no update about the status. So the LeoSat, medium Earth constellation with around 100 satellites was cancelled. OneWeb was went bankrupt, and then in the middle of last year, it's been restructured and brought back to life. 13B has 20 satellites in equatorial plane. It's operational. Another like subsidiary, mPower, is under development. Samsung also still did not disclose its plans for 4,600 satellites. However, also filled the application for frequencies. Starlink satellites, it's a little bit more than 540 satellites launched today by the absolutely huge constellation in different planes, in different orbits to provide broadband internet. Telesat, Viasat, and Telesat V-band are undisclosed or under development currently. Relating to challenges, there are 3 major challenges these constellations might face in the near future. I think we will go in more detail later in the presentation. A few statistical facts about this constellations. So if we accumulate them by satellite numbers, so most of the constellations have less than 50 satellites in them. Most of the proposed constellations, not only communication constellations, around 22% have from 50 to 150, and only 6% have more than 500 satellites on orbit. Regarding the satellite sizes, most of the satellites are nano, with a mass of less than 10 kg. 35% of them are medium, with a mass less than 100, and 17 are micro, with the mass from 10 to 100 kilograms. So what was in the past? So the idea of the constellation of satellite was pretty much 20 years ago, when Iridium and Globostars were the first one to provide satellite connectivity. They were offering communication links, and they were competing with terrestrial cellular network. Like today we can see who won this battle. Terrestrial cellular network were like the better fit into the market demand at that moment. Back in the 90s, the business model developed by Globostar and Iridium services was not sustainable enough due to like pretty small markets and high maintenance costs. And right now we're gonna go in detail to this constellation's history and the products. So the Globostar is an American satellite company. It's operating in LEO. It has 42 satellites right now on LEO orbit, and it provides communication phone and low-speed data communication. On this image, you can see the coverage of the Globalstar satellites. The company has 350,000 subscribers worldwide in 120 countries. Yeah, the coverage is almost global. Still some parts in the Arctics and in Africa are missing. Regarding products and application, Globalstar main part is to provide mobile satellite voice and data services. There's no internet, so it's not possible to use WhatsApp or Telegram or other internet based applications. However, product line includes mobile and fixed satellite phones, simplex and duplex satellite modems, airtime packages, and track and personal safety devices, which I personally used, and it was like super awesome. It's super small and quite precise. Yeah, so I was a satisfied customer of Globalstar. On this slide, you can see some other products. So the cellular phones, pretty big ones with big analog part, hotspots for Wi-Fi. That's I think pretty new products in their product line. Transmitters, development kits, go in educational, and some spot trackers for people, for asset management. The solar-powered asset management units, which is possible to attach, for example, to containers in the ships, and satellite transmitters. Regarding the applications, there are several land-based customer segments or assets and personal tracking. Globalstar is aiming to access like any remote areas beyond the reach of cellular and landline networks. So the customer segment include oil and gas, government, mining, forestry, commercial fishing. You can see the list of the rest on the slide. Asset and personal tracking is the basis of the supervisory control and data acquisition applications, and one of the possible applications might be like some extreme sports, people who are doing extreme sports. A few major facts in the history. So the project was launched in 91st as a joint venture. In 95th, it received the allocation of frequencies it's applied for. In 98, the first satellite was launched. Overall, the system deployment was a little bit delayed until later due to the launch failure of Soyuz. In 2000, it has been completed by the 52 satellites. There were 48 satellites and 4 spares. In 98, the first call of the Globalstar system was placed and the system was tested. In 99, system began the friendly user trials where the constellation of the satellites was completely utilized. In 99, so the complete commercial service with first 200 users began. In 2000, it became full commercial service within the North America, Europe, and Brazil. And the initial price was $1.79 per minute. In 2002, the bankruptcy came and non-sustainability of the business model was proved. However, in 2004, the Globalstar restructuring was completed and the company was back to life. In 2007, Globalstar launched another 8 spare satellites to compensate some like failured or lost satellites. From 2010 to 2013, there was a second generation of 24 satellites to restore the full potential of the service. And in March 2020, Globalstar has announced the third generation with capabilities of 5G like variant. Let's have a closer look on the satellites of the global star. On this picture, you can see the beautiful render provided by Thales Alenia Space Company. Basically, the satellites belong to the US for a communication application type. The contractor who built the satellite was Alenia Space. As for equipment, there were 16 S-band transponder and 16 L2C-band transponder. The Elite Bus 1000 was the basis of the satellite carrying this equipment. And as we will see later, this bus was used for many big satellite buses for communication purposes in the future. The power system consisted of two huge deployable solar arrays with 2.4 kilowatts at the beginning of life and batteries. The satellite lifetime was set to 15 years. The mass 700 grams. And as for orbit, the MEO orbit with 52 degrees inclination was chosen for the first part of the constellation and 920 kilometers for the phase in orbit. All right, we can see once again the picture on the right, the Elite bus with transponders installed on the satellite. So basically, the bus carried 2 GB mass memory with 690 kilobit per second S-band transmitter. For telemetry, the bus could be used basically for 500 to 1,500 kilometers. The precision altitude control was set to 0.05 with a set of sensors accommodated on the satellite. Right, which was the altitude control was fully redundant with radar, star tracker, GPS, reaction wheels, and magnetic talkers. All right, so that's the brief description of the global star service and the satellites, and we can jump to the next one, Iridium constellation. Iridium provides the constellation provides the L-band voice and data information coverage through phones, pagers in the past, and integrated receivers. Iridium owns and operates its own constellations and also sells equipment and services. So if you go to the website of Iridium, you'll see that they have two lines. One is dedicated to products and phones and trackers. Another one is complete service coverage. It was founded back in 1987, and 88 was protected by Motorola, and the fixed price contract was developed by Motorola from 1993. And in 1998, the system became operational and commercially available. So almost a little bit more than 10 years after it has been founded. The constellation consists of 66 active satellites, and they orbit in the Earth on the height of 781 kilometers with inclination of 86.4 degrees. And on the left, you can see the fleet, the render of the fleet of Iridium satellites. And on the right, you can see the coverage which the satellites are providing. Regarding applications, it's pretty much the same application fields that Global Star is targeting. So it's maritime, tracking of ships communication, voice calls from ships, IoT. A growing sector of IoT requires some connectivity not dependent on the cellular networks. Land mobile is also almost the same, and aviation almost the same what Global Star is providing. Yeah, and on the website is specifically targeted the US government as a separate field of applications for Iridium. Right. Land, Internet of Things, aviation, enterprise, government. It's all the places where the cellular network cannot be reached Iridium provides their solutions there. On the website, it's also possible to find there's a huge list of different products, starting from like small transceivers to phones, satellite phones, or to these kind of transceivers which can be installed on the airplanes. From plan details, it's possible to acquire monthly plan fee, like monthly plan with one of these phones, and like for 10 voice minutes, 10 text messages, the price is $56, and for 100 it's 90. It sounds quite a lot compared to the cellular networks we are all used to, or the internet we're having every day. Yes, however, yeah, it works. A few words about the history. So the Constellation was, the company was founded in early 90s. So the basic idea was to provide communication independent from mobile cellular networks. Early calculations showed that 77 satellites wouldn't be needed. That's where the name Iridium comes from, after the metal with atomic number 77. However, it turned out that just 66 satellites were required to cover all the planets. And yes, once again, on the left, you can see the satellites and the intersatellite links between them, and the full coverage of Earth and their intersections. The first generation Constellation was financed by Motorola, and the satellites were deployed from 97 to 2002. Iridium employed like pretty diverse fleet of satellites, taking different launch opportunities into account, like from US, Russia, and China. 60 satellites were launched on 12 Delta II rockets. 21 was launched on Proton, 2 on Rocket, 12 on Long March. And the first test telephone call was made in 1998, resulting in full global coverage in 2002. Even though the system was like working, functional, and from the technical perspectives, there were no showstoppers. This was absolutely not a success in the market due to insufficient demand at the price which was offered. So the company failed really badly to get the sufficient amount of revenues, thus resulting as one of the largest bankruptcies in the US history in general. However, the Constellation continued operational, continued being operational after the bankruptcy. After that, the new entity has emerged, a new product, including new product placement and updated pricing strategy. So idea was to provide reliable service in the places on the planet where traditional satellites cannot get access to. So from the 2002 to 2017, there were no new satellites on orbit at that moment. However, in January 2017, the second generation of Iridium satellites has been started. That was boosted by the huge $2 billion contracts with Thales Alenia Space Company. And here, like, we remember about that, the bus which was used for the Globostar, this was almost the same bus. SpaceX was contracted to launch the fleet of 81 satellites with Falcon 9. And deployment of this constellation began in 2017. In 2019, SpaceX launched additional 10 satellites and upgraded the amount to 75. In January 2020, Iridium was certified. That's actually a pretty cool thing to be used in global maritime distress and safety systems. The cool thing about this is that there was another company, British company, Inmarsat, which was holding this license for for a really long time, since 1999, and they were holding that like only by themselves. So that's a huge step, I think, from the business perspective to Iridium company. Here on the left, you can see like 8 satellites closing the fairing, like on the fairing, with encapsulator around it and preparation for the launch. The big point in Iridium constellation history is the collision which happened in 2009. So the Iridium with the satellite number 33, it collided with Russian satellite Cosmos 2251. That was pretty much the first huge hypervelocity collision between 2 artificial satellites in low Earth orbit. So they collided on a pretty high speed and created a huge amount of particles in the low Earth orbit. So here on the pictures, you can see the point of collision and debris after 20 minutes and after 50 minutes. And on this plot, it's much more observable, the spatial density of that's the biggest peak in the space debris density in low Earth orbit ever happened. So the orbit of 800 is quite dangerous right now to be on. So the first Iridium satellites were based on the platform LM700. A few details about that. The Iridium was the operator. Lockheed Martin was developing the bus as a contractor. The satellite had 2 big deployable solar arrays and batteries with a lifetime of 8 years, which is double less than a Globalstar had, with mass of almost 700 grams, and the orbit also double less than Globalstar with 86 degrees inclination. The satellite had 3-axis stabilized hydrazine boosted propulsion system. 2 solar panels which were moving to get direction to the sun, L-band transmitter to provide voice at 4.8 kilobits per second and data at 2.4 kilobits per second with a 16 decibel margin, which is pretty good. 48 spot beams were used for Earth coverage in Ka band for crosslinks and ground commanding. Regarding the next generation of the satellites, next Iridium constellation is going to consist of 66 satellites in 6 different planes. Targeted orbit is polar with 780 kilometers in inclination, like still same inclination. It's the next generation period was 2015 to 2016, and mission lifetime doubled to 15 years from 8 years. This time, to mitigate the risks, Iridium has some spare, like 6 in-orbit space and 6 hangar spares. Additionally to this, to the main mission of the satellite, it also carries radio occultation for measuring some atmospherical parameters, altimeters for monitoring the height of the sea, broadband radiometers for radiation belts, radiation budgets monitoring, multispectral imaging for ocean color imaging, and there are a couple of other potential missions area which can be targeted with this defined set of the payloads. Right, so here, this one is the next generation satellite. It's 860 kilograms with 2 kilowatt of power provided by solar panels. It's almost 10 meters when all the solar panels are deployed. Yeah, so for RF communications, it uses L-band and Ka-band, 48 beam transceivers, fast array antennas. Yeah, much more advanced compared to the initial LM satellite architecture. All right, so these were 2 examples of constellations built and founded back in 90s. And right now I'm going to cover 2 constellations which are younger, much younger, were started only last decade. OneWeb is the first one. Initially, it was planned to be a 650 satellite constellation. The initial plan also was to complete it in 2019, 2020, with a goal to provide internet broadband and to start the global services in 2001. So there were a couple of renamings and restructurizations in the story of this company. It was formerly known as World Wing Satellites, with like offices around the world. It was the constellation was aiming to occupy 18 orbital planes with 36 satellites on each, in the altitude of 1,200 kilometers and 87.9 degrees inclination. Another point in the constellation design was to make it scalable and to basically update the satellites in different orbital planes. The initial concept was to build the 150 kilogram satellites with electric ion propulsion. Each of the satellite could cover like 1,000 to 1,000 kilometer footprints. As main technology to provide this service, the Q and Ka bands were selected with 10 gigabits per second maximum capacity for the satellite. So compared to Globalstar and Iridium early developments, like several thousands of kilobits per second, this is way above that. So the main service areas would be remote small cell networks, mobile broadband with a speed up to 15 megabits per second and really low latency, around 15 milliseconds. That's basically the architectural representation of the service. So LEO-based constellation of the satellites connects user terminal, ground networks, and point of presences. User terminals are done via like small and compact devices and can be installed on plane ships, on home, or any other devices which require internet access. Yeah, so like from innovation perspective, like hydraulic scanning antenna vendors were one of the unique selling points of OneWeb for multiple beamforming and satellite tracking. Few words about the history. So the initial concept was born in May 2014. It included 20 satellites operating in 20 different orbital planes to provide internet coverage. In 2014, in June, this World War acquired the satellite spectrum owned by Skybridge, and the Skybridge is not a communication constellation provider which went bankrupt. Later, in 2014, there was a tender. So they issued a tender for manufacturers of the for the manufacturing of these 640 satellites, and at that moment also they already secured radio frequency spectrum. Actually, you can compare how from the start of the company until the RF spectrum licensing, only half a year have passed. When we were talking about Iridium, like 5 years have passed since they secured the frequency. So the process is really accelerated. In June 2015, there was a modification in the plan to deploy a larger constellation of 720 satellites and to increasing the orbit to 1,200 kilometers. In 2016, the idea went back to 704 satellites. In December 2016, the major investment came with 1 billion from SoftBank. And in 2017, maybe taking this amount of investment into account, the so the satellite constellation size increased to almost 2,000 satellites. Yeah, and then March there was a solid plan to add 2,000 more in V-band satellite for non-geosynchronous orbits, and that application for frequencies was also done at that moment. In December 2018, company backs up saying that they still need only 600 satellites. It's hard to imagine what was the motivation between these changes every year, changes in the amount of constellations. However, in February and March, OneWeb completed its first 2 successful launches of 34 satellites on the Soyuz rocket. However, in the March of last year, OneWeb affiliating and filing the bankruptcy with difficulties raising another round of capital and deploying like 90% of the network of the satellites. In July last year, the UK government and Party Global won the auction to buy the company and invest. There was an investment of 7 billion, and basically this year on 15th of January, like actually several days ago, yes, like 5 days ago, there was an announcement of additional funding from SoftBank of additional $1.4 billion, which will, based on what is OneWeb management is saying, which will be enough to deploy the rest of the satellites by the end of 2022, which I'm a little bit suspicious about. And on the right here, you can see the satellite bus and the satellite preparation procedures on the Cosmodrome. In order to build this huge amount of satellites, OneWeb built the huge manufacturing facility in Florida. It's like almost 14,000 square meters in size. Huge area of it dedicated for integrations and test of the satellites. Right, but I can mention here that production of 900 satellites in total was planned for this facility with peak production rate of 1-2 satellites per day. That's really crazy amount of satellites. But we will see in SpaceX is even more ambitious. Here you can see the first satellites in the Toulouse, in Airbus, which are ready for shipment, like big transponders, stoked solar panels. A few words about the platform. So the platform is called Arrow for the constellation. It aims to go to LEO at 1,200 kilometers. Launch mass of the 34 satellites together is 5 tons. As propulsion, it uses plasmic propulsion system, lithium-ion batteries. There are 2 Omni antennas, 2 Q-band antennas, and 2 Ka-band antennas. For stabilization, it incorporates 3-axis control system. It's really impressive how the fairing with a lot of satellite looks like. I think people are so small. And yeah, and a few words about the Arrow platform. You can see here, I will share the slides afterwards, and you can have a closer look. I will just continue because we don't have much time left. Starlink constellation is I think the most ambitious and the most the most famous constellation everybody is aware. And last summer, I think a lot of people have seen the snakes of stars crossing the sky. So the Starlink is the constellation to provide internet. The constellation will consist of thousands of mass-produced satellites on LEO. And the production rate of SpaceX is currently 120 satellites per month, which is enormous. This is the initial plan for the Starlink constellation. We can see that it covers like absolutely all the Earth with 1,584 satellites in 72 different orbital planes. This is the plot with satellites on the orbit since May 2019. And we can see that every launch, yeah, so in total there were almost 900 satellites launched. In October 2020, the amount of satellites decreased. This is due to the test of the orbiting system. So actually SpaceX has taken this topic of space debris quite seriously, proving that after end of life, the satellites will be able to deorbit and decommission. All right. The initial 12,000 satellites were planned to occupy 3 different orbital shells. You can see there which bands they would occupy and how many of the satellites would be. And on the right, you can see the fairing, almost encapsulated fairing with Starlink packed satellite assembly. A few words about the history as well. So the SpaceX was announced in January 2015, like actually a couple of months later after the OneWeb was announced. In November 2016, already SpaceX filed application for NGSO with fixed satellite service using Ku and Ka bands. In March 2017, filed the plans for another 7,500 for V-band satellites. In November 2018, approval was received to deploy this 7,518 broadband satellites. June 2019, there was another frequency application for another test of 270 ground terminals. So SpaceX is also deploying a huge ground station network around the world. In November, as of November 25th, SpaceX has launched almost 1,000 Starlink satellites. These are just like really impressive numbers. As for today, total amount of satellites launched is 955. 64 satellites were deorbited for experimental purposes. So right now there are 891 Starlink satellites on orbit. A few words about the satellites themselves. The really detailed information is not as available as about OneWeb or Iridium or Global Star satellites. But what we know is that the mass is 227 kilograms. So the design is the flat panel, and the huge antenna, array antenna, is deployed in a single array solar panel. Satellites are using Hall effect thrusters with krypton as the reaction mass. They use star tracker for precision. 95% of components are quickly burning in the atmosphere. There's like eco satellite, self-decomposing satellite in the orbit. And these satellites are using optical intersatellite link and phase array beamforming for processing Ku and Ka bands. So they are pretty smart about the RF spectrum and like availability of frequencies. So optical communication is also the core of the service. The first 60 satellites were launched in November 2019. The 60 satellites which were launched in November, they had this additional characteristics. So Ka band was not added to the satellites before, so then mass increased and their beta reduced, and I will talk about that a little bit later. On this picture, you can see like the table with planned number of satellites per orbit shells and satellites operational. Here you can also see when the planned half-size completion time will be achieved, or the full-size completion time will be achieved. So by 2027, pretty much all the satellites are supposed to be on the orbit, and right now SpaceX is also only filling the first orbit, and it's halfway to go still. Signal pollution is a big topic regarding, in general, communications constellations, in general, small satellite constellation. If we think that they're going to be 10,000 satellites soon, and in case they're using ion thrusters as Starlink satellites are using, the level of pollution in visual spectrum is gonna increase significantly. And these pictures are done with like radio telescopes, and we see that scientists might get really annoyed by this pollution. This is why in the next next generation satellites of Starlinks, albedo was significantly reduced. Right, so we have 5 minutes left of the lecture, and I'm gonna conclude this with future challenges of constellations. So basically, large constellations, not only communication, but Earth observation as well, they are going to face maybe 3 major challenges. First one is technical, management, and regulatory. And as proposed solutions, there can be optimization of automatic satellite tracking or automatic failure detection. And we're going to go through these topics in more detail right now. From the constellation management, it might make sense to split the tasks between payloads and spaceport operations, and dedicating the ground segments for each of these 2 tasks. So splitting the tasks for the ground station between these 2 big blocks of tasks. The automation on board of the spacecraft might be increased. This is in terms of failure tolerances, maybe self-decommissioning, and so on. Taking not only the ground segment into account, but operations from the early design stages, from the early constellation design, might also help to solve problems in the later stages. And expert systems shall be designed to assist operations. For example, mitigating the heavier workload during the launch and early orbit phases. Communication is the key of the constellation services, communication and low latency. And onboard automation is unlikely to grow as to provide autonomous fleet management. The large amount of satellites will still need to conduct communications with ground stations. The constellations are designed usually for the real time and for like 24/7 purposes, and they might require big data to upload or download at any time. Solutions here might be infrastructure optimization, as I said, using the splitting the ground station tasks, or utilization of 5G services, or avoiding radio spectrum and using the optical communication technology here. Regarding space traffic management, there's, as we've seen with Iridium, space debris can become a hot topic. As for solutions, there might be alternative devices or alternative services for active removal and space-based surveillance networks. And here you can see 2 proposals for active debris removal devices or satellites, or on-orbit servicing with an option to decrease the amount of their satellites. However, this approach is pretty costly and technologically challenging, so this will include like docking, orientation determination of the satellite, and so on. So in the space traffic management, the first solution it looks much more attractive. Regarding the technical challenges, machine learning might support some machines due to health and address management issues. Neural networks can enhance space traffic management regarding this huge amount of satellites in orbit. And space transponders can be enhanced by using the corner reflectors on board GPS receivers for better satellite tracking. And as a conclusion, I would like to say that the general trend has been noticed in launching big constellations of small satellites. So it's clear, and it was well established for the last 2 decades. Small satellites are the core of this constellation idea, as they're not so big and they're pretty easy to develop and much cheaper to launch. Spacecraft constellations are appealing in major fields: communications for global coverage, Earth observation for near real-time measurements, and space observation for continuous monitoring and surveillance. And yeah, it's going to be exciting time. New service is going to be available, especially looking forward to the satellite internet provision. All right, I hope you enjoyed it, the second day as well as the first one. If you have any questions, I will be happy to answer them.
Thank you. Okay, any questions to our lecturer?
Any questions or feedback? Yeah, feel free.
About feedback, thank you very much. Okay, just for questions. Okay, if there's no questions, please again about presentations. Can you share them with us?
Yeah, so I will share both of them, together.
It would be great.
Yeah, just curious, which topic did you like more the first day? CubeSat general, then CubeSat specifics, or constellation topic?
So if there is no answers for myself, the second day is more, because it is, how to say, more with applications and future demands, and I mean what's going on for now and what would be in the future. That's why for me the second is more interesting for me. Yeah.
Okay, that's a very, yeah, passive.
Abdulaziz also says second day.
Yeah. Yeah, please write in the chat constellations. Okay. Yeah. Good to know.
Thank you very much. Спасибо большое. And good luck. Have a good day. And I hope, how to say, our collaboration would be fruitful. And we'll wait for future collaborations. Спасибо большое.
Да, спасибо большое. Да, надеюсь, еще увидимся. Да.
Спасибо, очень интересная лекция.
Спасибо. До свидания.
До свидания. Спасибо большое. Я отвечаю вам.